did the Romans manage to make water flow uphill? This intriguing misconception actually hides an even more impressive truth. The truth about precise calculations, gravity, and unparalleled engineering genius. The Romans did not defeat the laws of physics. They subjugated them with such precision that it still inspires awe today. They created arteries of stone and concrete that carried life to their vast cities, feeding fountains, baths, and homes. Watch the video to the end, and you will learn how Roman engineers, using only simple tools and fundamental principles, were able to build kilometers-long waterways that functioned reliably for centuries. What if I told you that aqueducts were not built solely to quench thirst? In fact, water in ancient Rome was much more than just a resource for survival. It was a currency, a status symbol, and a powerful tool of political control. Having a clean, abundant, and constant source of water was direct proof that a city was protected by civilization. Early Rome was completely dependent on the Tiber River, but as the city grew, its waters became increasingly polluted. The first aqueducts, such as the Aqua Appia, were built primarily to meet the basic needs of the population. However, the Roman elite soon realized the potential of water as a demonstration of power. The presence of an aqueduct meant that the city was capable of conquering nature and harnessing its resources for its own use. For wealthy citizens, connecting to the water supply was the ultimate sign of luxury. While ordinary citizens carried water from public fountains, patricians could afford private baths and decorative fountains in their villas. Obtaining permission for a private connection was a complicated and expensive process, making water a visible divider between social classes. Emperors quickly realized that control over water meant control over the population. The construction of new aqueducts and huge public baths, or thermae, was a popular political move. This demonstrated the ruler's generosity and concern for the people, ensuring the loyalty of the masses. The baths were not just a place to wash, but entire social centers accessible to virtually everyone. Water also played a crucial role in the economy and even in the military. Huge amounts of water were required for industrial processes, such as mining. The Romans used a method known as hushing, in which pressurized water jets were used to wash away rock and extract ore. This required the construction of complex temporary aqueducts in remote regions. The monumentality of the aqueducts themselves served as propaganda. The huge arches crossing the valleys were visible from afar and served as a constant reminder of Rome's power and engineering prowess. They made a lasting impression on both citizens and conquered peoples. It was architecture that asserted its dominance. Interestingly, aqueducts also became targets during wars. Destroying an aqueduct was one of the most effective ways to besiege a Roman city. By cutting off the water supply, the enemy could quickly bring the defenders to their knees. This further emphasizes how vital this infrastructure was to the city's survival. Thus, each new aqueduct was not just an engineering project, but a political statement. It strengthened the emperor's power, stabilized society, and demonstrated the superiority of Roman civilization. Water flowed through the channels, not just for the sake of it. It flowed at the behest of Rome. This complex system required constant supervision and management. Special government services were created, such as the Cura Aquarum, which was responsible for the construction and maintenance of aqueducts. This service was headed by a high-ranking official, the Curator of Waters, which emphasizes the state importance of this resource. We can see that the aqueduct was at the heart of Roman ideology. It combined practical necessity, social function, and political propaganda. Without this continuous flow of water, Rome as we know it simply could not have existed. We are very interested to hear your opinion. Which function of water, social, political, or economic, do you think was most important for Rome? Write about it in the comments and don't forget to subscribe to our channel. Are you ready to learn the truth about how the Romans literally read the earth to find water? The success of any aqueduct began not with the first stone, but with the first step of the Aquiligia, a person whose profession was to search for water. These specialists had a deep knowledge of geology and hydrology, albeit based on centuries of observation rather than modern science. Choosing the source was perhaps the most important decision in the entire project. The water had to be not only abundant, but also clean, and the source itself had to be located high enough. This was the only way to ensure the necessary slope for gravitational flow along the entire length of the multi-kilometer route to the city. Engineers preferred to find underground sources or mountain springs, as their water was cleaner and had a more stable temperature. Roman engineers and aquilai were true masters of observation. They studied the landscape, paying attention to vegetation. Certain types of plants that remained green even during the dry season could indicate the proximity of groundwater. They also looked for fog rolling in the lowlands in the morning, which could also be a sign of moisture. The architect and engineer Vitruvius, who lived in the 1st century BC, left detailed descriptions of methods for finding water. He advised lying down on the ground at dawn and with your chin to the ground, looking for vapors rising from the soil. Where they were most noticeable, test drilling should begin. It was a simple but effective method of detecting moisture. Once a promising location was found, the testing phase began. Workers dug test pits, or puteoli, to assess the actual volume and quality of the water. They observed how quickly the pit filled, how clear the water was, and whether it had an unpleasant smell or taste. Sometimes water from a new source was given to local residents to taste to ensure its safety. Water quality was paramount. The Romans valued water that was cold, clean, tasteless, and odorless. Engineers conducted simple tests. They boiled the water and checked whether any sediment remained at the bottom of the vessel. They also paid attention to the health of people already using the source. This was the most reliable indicator of its suitability. Sometimes entire drainage tunnel systems had to be built to collect water from several small sources. These tunnels, laid underground, collected groundwater and directed it into the main aqueduct channel. Such a system was complex to build, but it guaranteed a stable and abundant flow. Once a source was finally approved, an equally complex legal process began. The Romans sacredly revered private property rights. Engineers had to negotiate with the owners of the land through which the aqueduct was to pass to purchase or lease the territory. This was often more difficult than solving any technical problem. Accuracy in estimating the height of the source was critical. The engineer had to calculate not only the difference in height between the source and the final point in the city, but also the entire future route. A mistake at this stage could render the entire multi-million-dollar project useless. Therefore, even at the stage of searching for water, surveyors actively used their measuring instruments. Thus, the search for a source was a complex, multi-stage task that required a combination of geological knowledge, observation, and engineering ingenuity. The Romans weren't just looking for water, they were looking for the perfect water to feed a great city. It was a huge job, hidden from view, but it was the foundation for all the construction that followed. Which of these ancient methods of finding water do you find most ingenious? But finding water is only half the battle. In the next chapter, we will reveal the main secret of Roman engineers, how they made water flow for tens of kilometers with an almost perfect slope, using tools that will seem ridiculously simple to you. I will reveal the most closely guarded secret of Roman engineers. It is not magic or the conquest of the laws of physics, but the triumph of precise calculation and one ingenious tool. The whole secret of aqueducts lies in one word: gravity. Water flows downhill, and the Romans perfected this simple principle to absolute perfection, creating a slope that was almost invisible to the eye but worked flawlessly. The main tool that made this incredible precision possible was the horavat. Imagine a long, about 6-meter-long wooden beam, perfectly aligned and mounted on 4 legs. A shallow groove was carved into the upper side of the beam. This simple device was the pinnacle of Roman geodesy and the main secret behind the construction of aqueducts. The principle of the horabatus was ingenious in its simplicity. Water was poured into the groove. If the water touched both edges of the groove evenly, it meant that the beam was perfectly horizontal. In windy weather, when the water could fluctuate, engineers used plumb lines hanging from the sides of the beam. When the plumb lines coincided with the marks carved on the legs, this also confirmed the horizontality. Using a level, engineers could measure and maintain the desired slope. They moved the instrument step by step from one point to another over tens of kilometers. At each step, they used wedges under the legs to achieve not a perfect horizontal, but the desired, barely noticeable slope toward the city. It was painstaking, slow, but incredibly accurate work. Roman engineers empirically calculated the ideal slope. It could not be too steep, lest the fast flow of water destroy the canal walls, but it couldn't be too gentle, so that the water wouldn't stagnate and bloom. The optimal slope was considered to be 1 to 3 meters per kilometer of the route. This is a negligible difference, requiring precision. For example, the famous Pont du Gard aqueduct in France, part of the 50-kilometer water pipeline in Nîmes, has an average slope of only 34 centimeters per kilometer. Over its entire length, it descends only 17 meters. Maintaining such a slope over rough terrain, through tunnels and bridges, using only a plumb bob and a spirit level, is a true marvel of Roman engineering. For more complex measurements, such as when laying tunnels or determining angles, another instrument was used, the diopter. It was a more complex device, similar to an early theodolite. It allowed both horizontal and vertical angles to be measured, which was necessary when planning a route through hills and valleys. Another important tool was the groma. It was used to mark right angles and straight lines on the ground. The groma was a cross with 4 plumb lines. It was indispensable for marking camps, roads, and of course, the initial sections of aqueducts. But it was less useful than the horabat for maintaining a slope. The entire construction process was a series of thousands of tiny, precise measurements. Surveying engineers, or grommatici, were among the most respected and highly paid professionals in the Roman Empire. The success of the entire multi-million-dollar project depended on their accuracy. A 1-centimeter error at the beginning could turn into meters of useless deviation at the end. Thus, the secret of aqueducts is not victory over gravity, but its masterful use. It is a triumph of patience, methodicalness, and ingeniously simple tools, which in skilled hands made it possible to create structures that have survived for millennia. The Romans did not build until they had measured 7 times. If you admire the precision and genius of Roman engineers, please like this video and be sure to subscribe to our channel so you don't miss new videos with fascinating stories about ancient Rome. Guess how long it took to build this? The construction of the aqueduct was one of the most ambitious and expensive projects the empire could undertake, comparable in cost to a major military campaign. It involved thousands of people, from highly skilled engineers to legionnaires and laborers. It was a veritable army, armed not with swords but with picks and shovels. The legions often played a leading role in construction. In peacetime, soldiers were the main labor force of the empire. They possessed discipline, organization, and the necessary engineering skills. Legionnaires built roads and bridges, dug tunnels, and erected arches for aqueducts. Their participation also ensured the protection of the site from possible attacks. In addition to the legionnaires, a huge number of local workers and specialists were involved in the work. These were bricklayers, carpenters, blacksmiths, as well as unskilled workers who did the hardest work, digging trenches, carrying stones, and mixing mortar. Managing such a large number of people required outstanding logistical skills. The tools used by the builders were simple but effective. The main tools were iron picks, hoes, shovels, and scoops for earthworks. Hammers, chisels, wedges, and saws were used to work with stone. Blacksmiths repaired and sharpened tools on site, ensuring uninterrupted work. The route planning process was incredibly complex. Surveyors, known as grommatici, walked the entire route dozens of times, hammering in pegs and marking out the future route. They tried to route the aqueduct along the slopes of hills, following the natural contours of the terrain. This was cheaper than building bridges or digging tunnels, but it lengthened the route. When a hill stood in the way, the engineers had 2 options: go around it or dig a tunnel. Digging a tunnel was a laborious and dangerous task. Workers used a technique called fire drilling. They lit fires near a stone wall and then rapidly cooled it with water or vinegar. The temperature difference caused the stone to crack, and it could then be broken up with pickaxes. To ensure accuracy, tunnels were often dug from both sides at the same time. To meet at the right point, surveyors dug vertical shafts at the top of the hill. These shafts served not only to check the direction, but also for ventilation and to lift rock to the surface. Despite all these precautions, small discrepancies at the junction were common. If a valley or river blocked the way, the builders erected an aqueduct bridge. These structures, with their majestic arches, became a symbol of Roman engineering. First, carpenters built giant wooden scaffolding, or centers. This scaffolding served as a temporary support for the masonry until the keystone was laid in the center of the arch. Each stone for the arch was cut with incredible precision. The masons worked in quarries, often located many kilometers from the construction site. The finished blocks were marked and delivered to the site by ox carts or by river on barges. At the construction site, they were lifted to the required height using wooden cranes powered by human strength. Logistics was key to everything. It was necessary to ensure the uninterrupted supply of materials: stone, sand, lime, and wood. It was also necessary to feed and house thousands of workers. This entire complex system functioned as a single mechanism, subordinated to a single goal: to deliver water to the city as quickly as possible. Which aspect of aqueduct construction do you find most challenging? The precision of measurements or the management of thousands of workers? In the next chapter, you will learn how the Romans built arches that still stand today. The truly ingenious answer was a complex combination of incredibly practical design principles and a deep understanding of natural properties honed over centuries. The construction of aqueducts was not only an engineering challenge, but also an architectural one. When the Romans encountered a valley, ravine, or river, they did not retreat. They built their famous aqueduct bridges over the obstacle, which still amaze us today with their grace and strength. The secret of these structures lies in an ingenious invention: the semicircular arch. The Romans did not invent the arch, but they perfected its use. The arch allows large spans to be covered using relatively small stone blocks, or wedges. The weight of the masonry above the arch and the arch itself is distributed along its arc and transferred to the side supports, or abutments. This design is incredibly strong and economical. Building an arch required tremendous skill on the part of the carpenters. First, they built massive wooden scaffolding called centers. This scaffolding precisely replicated the curve of the future arch and served as a temporary support for the stone blocks. The quality of this wooden structure was critically important, as it had to support the weight of thousands of tons of stone. The masons laid the wedges of the arch on both sides, moving towards the center. The last central stone, called the keystone, was hammered into place and closed the structure. After that, the arch became self-supporting, and the wooden scaffolding could be dismantled. This moment was a real triumph for the builders. Often, to cross a particularly deep valley, the Romans built multi-tiered arcades. The most famous example is the Pont du Gard in France. This aqueduct consists of 3 tiers of arches, with the lower, wider ones serving as the foundation for the upper ones. This design was not only sturdy, but also saved material by creating openings. However, most of the aqueduct was hidden from view. For example, of the 50 kilometers of the total length of the aqueduct in Nîmes, only a small part runs across the famous bridge. About 80% of Roman aqueducts ran underground. This was cheaper, safer, and more practical than building above-ground structures. Underground channels, or specus, were laid in trenches and then covered with stone slabs or arches. This protected the water from contamination, evaporation in the sun, and even from enemies who might try to poison the water. The channel was always slightly higher and wider than necessary for the flow to facilitate access for maintenance. When a hill stood in the way, engineers preferred to dig a tunnel. This was one of the most difficult and labor-intensive tasks. Roman tunnel engineers, or minatori, were highly skilled specialists. They used picks, wedges, and hammers, slowly advancing into the hard rock. To ensure accuracy, tunnels were often dug from both sides, towards each other. To ensure the correct direction, surveyors marked a line on the surface and then dug vertical shafts. These shafts were used for ventilation, rock removal, and direction verification. Small discrepancies at the junction were normal and were corrected on the spot. This underground work required tremendous courage and perseverance from the workers. They labored in darkness, by the light of oil lamps, in poorly ventilated conditions. Nevertheless, they dug kilometers of tunnels through the rock, demonstrating incredible persistence in achieving their goal: to bring water to the city at any cost. What if everything you've been taught about stone construction is outdated? While the majestic arches of aqueducts were often built of hewn stone, the Romans' real secret weapon was a material they perfected: We're talking about Roman concrete, or opus cementitium. This material changed architecture forever and allowed the Romans to build faster, cheaper, and on a scale never seen before. Roman concrete consisted of three main components: aggregate, such as crushed stone or broken brick; a binding agent, lime; and water. But it also had a secret ingredient, pozzolan. This is volcanic ash that the Romans extracted in the Pozzuoli area near Naples. It was pozzolan that gave Roman concrete its unique properties. When mixed with lime and water, pozzolan reacted chemically to form an incredibly strong and, most importantly, water-resistant compound. Unlike simple lime mortar, Roman concrete could set even underwater. This made it the ideal material for building the foundations of bridges, harbors, and of course, aqueducts. The use of concrete radically changed construction technology. The Romans no longer needed to carve huge stone blocks with perfect precision. They could build two thin walls of stone or brick, which served as a form or formwork. The space between these walls was then simply filled with concrete. This technique, called rubble masonry, was much faster and required less skilled labor than masonry with hewn stone. It allowed for the construction of gigantic structures in a relatively short time. The foundations and supports of aqueducts were often made of concrete, which was then faced with stone to give it a more noble appearance. However, the Romans still preferred stone for the arches and supporting structures themselves. They were masters of stone masonry, or opus quadratum. This method involved the use of large, precisely fitted rectangular stone blocks. The joints between them were so thin that a knife blade could not be inserted between them. The stone for construction was quarried as close to the site as possible. The masons used iron wedges, which they drove into holes pre-drilled in the rock. By driving the wedges in evenly, they broke off huge blocks from the massive. These blocks were then roughly hewn on site to reduce their weight during transport. Transporting these multi-ton blocks was a separate logistical challenge. They were loaded onto sturdy ox-drawn carts or, if possible, floated down rivers on barges. At the construction site, complex wooden cranes with a system of blocks and winches operated by workers were used to lift the blocks to great heights. On site, masons made the final precise adjustments to the blocks. They used plumb lines, levels, and squares to achieve a perfect fit. Often, the blocks were joined together with metal brackets that were filled with lead to prevent corrosion. This technique ensured incredible strength and durability of the structures. The combination of these two technologies, flexible and fast-setting concrete for massifs and foundations, and durable monumental stone for arches and cladding, was the key to the success of Roman engineering. They took the best from each material, creating structures that not only served their purpose, but also served as a symbol of Rome's unshakable power. Which of these materials do you consider more revolutionary for its time? Concrete or perfectly fitted stone? In the next chapter, we will look inside the aqueduct itself and learn how the Romans protected water on its long journey. When we look at aqueducts, we see majestic arches, but we rarely think about the most important part, the channel through which the water flowed. This channel, or spicus, was the heart of the aqueduct, and its design was thought out down to the smallest detail. It was not simply a trench carved into the rock, but a complex engineering structure designed to protect and preserve the quality of the water. The spicus was usually rectangular in shape and spacious enough for a person to move around inside. This was necessary for regular inspection and cleaning. For example, the canal of the famous Ponte de Gar aqueduct is 1.8 meters high and 1.2 meters wide. The water never completely filled the canal. Engineers left free space so that the flow would not be too turbulent. The biggest problem for engineers was waterproofing. Any leak meant the loss of precious water and could lead to the destruction of the structure itself, especially in winter. To make the channel completely waterproof, the Romans used a special mortar known as opus signum. Opus signum is another ingenious invention, a type of Roman concrete. It was made by mixing lime, sand, and most importantly, finely crushed brick or ceramic tile. This pinkish mixture was not only incredibly strong, but also completely water repellent. Workers manually coated all the inner surfaces of the canal with several layers of it. The walls and bottom of the canal were carefully smoothed to reduce friction and prevent turbulence. The smooth surface also prevented algae and other debris from sticking to the walls. It was painstaking work, but the efficiency of the entire aqueduct depended directly on its quality. The canal was almost always covered with stone slabs or a small stone arch. This was done for several reasons. First, the roof protected the water from leaves, dust, and other debris. Second, it prevented the water from evaporating under the hot sun, which was especially important in southern regions. Third, the covered canal prevented people and animals from using the water along the way, and also protected it from deliberate poisoning during wars. Water was a strategic resource, and its safety was paramount. Thus, the water traveled to the city in complete darkness and purity. Despite all the precautions, a problem arose inside the canal over time. The water carried by aqueducts, especially from underground sources, was hard and contained many dissolved minerals, mainly calcium carbonate. Over time, these minerals settled on the walls and bottom of the canal, forming solid deposits known as sinter or travertine. This sinter gradually narrowed the channel's clearance, reducing the flow of water. If left unchecked, the aqueduct could become completely overgrown from the inside and cease to function. Therefore, the Romans developed an entire maintenance system. Vertical shafts or inspection hatches were installed at regular intervals along the entire aqueduct. Workers called aquarii descended into the canal through these hatches. They used special picks and scrapers to chip away and remove solid mineral deposits. It was hard and dangerous work in a cramped, dark, and damp space, but it was absolutely necessary to maintain the city's viability. Sometimes the Romans deliberately gave the aqueduct a rest by shutting off the water supply and allowing the canal to dry out completely. Once dry, the sinter became more brittle and easier to remove. This shows how well they understood the properties of the materials they were working with. The journey of the water did not end at the city walls. Upon reaching its destination, the aqueduct flowed into a monumental structure called a castellum aquae, or water castle. This was the main distribution reservoir, which served to purify, store, and distribute water throughout the city. These structures were not merely utilitarian, but were often richly decorated, serving as a symbol of the city's wealth. The first task of the castellum was to purify the water. Before entering the main reservoir, the water often passed through several sedimentation tanks, or piscine limaria. In these pools, the flow rate dropped sharply, and any suspended particles, sand, silt, or other debris that had entered the water along the way, settled to the bottom. The pools were cleaned regularly to maintain water purity. After the settling tanks, the purified water entered the main distribution tank. Inside the castellum was an ingenious and socially significant distribution system. As a rule, 3 main pipes of different heights emerged from the tank. This design was thought out to the smallest detail and reflected Roman priorities. The lowest pipe, which always received water, even at the weakest flow, fed public fountains. This ensured that the general population, who did not have private homes with running water, always had access to drinking water. This was an absolute priority for maintaining social order and the health of the townspeople. The middle pipe, which received water if its level was sufficient, was directed to public baths, thermae, and was also used for the needs of the city, such as flushing sewers. The thermae were the center of public life, and their smooth operation was important for the mood of the citizens. Only the uppermost pipe, which received water last when the aqueduct was full, led to private consumers. These were the villas of wealthy citizens, craft workshops, and other commercial enterprises. These users paid a special tax for water, the amount of which depended on the diameter of their pipe. This hierarchy ensured that in the event of drought or aqueduct failure, when the water level dropped, private paying users were the first to be left without water. Public fountains continued to operate until the very end. It was a fair and far-sighted approach to resource management. A complex network of underground pipes spread from the castellum throughout the city. The main pipelines were made of stone or ceramics. However, for the final distribution to buildings and fountains, the Romans used lead pipes, or fistulae. They were easy to manufacture, solder, and bend as they were laid through the streets of the city. The production of these pipes was standardized. They were made by rolling a sheet of lead around a wooden mold and soldering the seam. The pipes were often stamped with the name of the manufacturer, the official who issued the permit, and sometimes the owner of the house. Today, these stamps are an invaluable source of information for historians. To regulate the flow to private users, the Romans used a calyx, a special bronze nozzle or pipe of standard diameter. It was installed at the outlet of the distribution tank. The size of the calyx was strictly regulated and served as the basis for calculating the water tax. Attempts to install a pipe with a larger diameter were considered a serious crime. Managing this complex urban network was a separate task. There were secondary distribution towers that helped maintain pressure and deliver water to different areas of the city, especially if it was located on hills. The entire system required constant monitoring and repair. Thus, the Castellum Aquae was not just a reservoir, but the brain of the entire city's water system. It transformed the wild flow coming from the mountains into an orderly, controlled, and fairly distributed life force that nourished every corner of the Roman metropolis. The arrival of water in the city completely transformed the daily life of its inhabitants. Aqueducts were not just an engineering marvel, they were a source of civilization, hygiene, and public life. The impact of this constant flow of clean water was felt everywhere, from luxurious villas to crowded streets. The most noticeable feature was, of course, the public fountains. They were scattered throughout the city, usually at every intersection. These were not just water collection points, but centers of community life in the neighborhood. Neighbors would meet here and exchange news. For most city dwellers living in cramped apartment buildings called insulae, the fountain was the only source of drinking water. But the real heart of Roman water culture was the thermae, huge public baths. These were not just baths, but entire leisure complexes, including pools with hot, warm, and cold water, steam rooms, gymnasiums, libraries, and gardens. Thanks to the aqueducts, the baths could serve thousands of visitors daily, with a nominal entrance fee or no fee at all. The engineering of the baths was no less impressive than that of the aqueducts. The water was heated in huge bronze boilers. The floors and walls of the steam rooms were heated using a hypocaust system, underfloor heating, where hot air from the furnaces was supplied through channels. This required a tremendous amount of water and firewood, but the Romans spared no resources for this important social institution. Wealthy Romans who lived in domus, private houses, or villas could afford the luxury of having running water directly in their homes. Water flowed into their courtyards, feeding private baths and decorative fountains. These fountains were not only decorative, but also served as a natural air conditioning system, cooling the air in the summer heat. Water was used not only for drinking and washing, but also for industrial purposes. Numerous craft workshops operated in cities, dyeing, tanning, and laundry, fulonici, which consumed enormous amounts of water. The availability of running water was one of the factors contributing to the economic prosperity of Roman cities. The abundance of water allowed the Romans to solve another important hygiene problem: waste disposal. Rome had a complex sewage system, the crown jewel of which was the Cloaca Maxima, or Great Sewer. This huge canal, originally built to drain swamps, became the main artery of the city's sewage system. A constant flow of water from aqueducts was key to the system's operation. Excess water from fountains and baths was deliberately directed into sewer channels. This powerful flow washed sewage from the city into the Tiber. It was one of the world's first continuous sewer systems, which significantly improved sanitary conditions in the overpopulated city. Of course, the system was not perfect. Access to the sewer system was mainly limited to public toilets, latrines, and the homes of wealthy citizens. Most residents of the insulae still used chamber pots. Nevertheless, the very existence of such a large-scale system was a direct result of the success of the aqueducts. We can see that aqueducts were not just pipes, they were a circulatory system that nourished all aspects of urban life. They provided hygiene, leisure, social interaction, and economic activity. Water was the foundation on which the entire complex structure of Roman society was built. Without aqueducts, Roman cities would not have been able to grow to such enormous sizes. It was the constant flow of clean water that made it possible to support the lives of hundreds of thousands, and in Rome, up to 1 million people, in a relatively small area. It was infrastructure that literally created Roman civilization. The aqueduct was not simply built and forgotten. It was a complex and vital organism that required constant care, management, and protection. The Romans understood this perfectly well, and created one of the world's first specialized government services, the Cura Aquarum, or Water Care Service. It was an entire department responsible for all aspects of water supply. At the head of this service was a high-ranking official, the Curator Aquarum. It was an honorable and very responsible position, often entrusted to former consuls or people close to the emperor. One of the most famous curators was Sextus Julius Frontinus, who carried out a large-scale reform of the water management system at the end of the 1st century AD. Frontinus left us with his invaluable work on the Aqueducts of Rome. In this book, he described in detail all 9 aqueducts that supplied Rome at that time, their length, capacity, sources, and problems. He also described the staff of the service, which included engineers, inspectors, surveyors, and hundreds of workers, aquarii. These aquarii were divided into brigades and were responsible for their sections of the aqueducts. They patrolled the route, looked for leaks, cleaned the channels of sinter and debris, and repaired damaged sections. It was a constant, year-round job, without which the system would quickly fall into disrepair. Roman law strictly protected the aqueducts. A sanitary zone was established around the above-ground parts of the aqueduct, where it was forbidden to build, plant trees, or engage in any activity that could damage the structure. Stealing water from the aqueduct by means of illegal tapping was considered a serious crime and was punishable by heavy fines. Frontinus proudly wrote in his book about how he fought against illegal connections that deprived the city of a significant part of its water. He personally inspected the canals, checked the diameters of the pipes, and brought order to the system. His work shows how seriously Rome took the management of its resources. After the fall of the Western Roman Empire, this complex management and maintenance system collapsed. Aqueducts, deprived of constant care, gradually fell into disrepair. The canals became clogged with synth, and the arches collapsed. Deprived of clean water, cities quickly fell into decline, and the population returned to using rivers and wells. However, the engineering genius of the Romans was not forgotten. Many aqueducts proved so durable that they survived centuries of neglect. Some, such as the aqueduct in Segovia or Pont du Gard, remain almost intact to this day, arousing the admiration of tourists and engineers alike. Moreover, some aqueducts have been restored and put back into service. For example, the Aqua Virgo, built during the reign of Augustus, was repaired during the Renaissance and, under the name Aqua Virgin, still feeds the famous Trevi Fountain in Rome. This is living proof of the quality of Roman workmanship. The legacy of Roman aqueducts is enormous. They did not just supply cities with water, they were a symbol of power, an instrument of civilization, and a monument to engineering thought. The principles laid down by Roman engineers, precise calculation of slope, use of gravity, durable materials, and constant maintenance, are still the basis of modern hydraulic engineering today. We have taken a long journey, tracing the path of water from a distant mountain spring to the fountains and baths of ancient Rome. We have seen that behind every majestic arch and every liter of clean water lay incredible labor, precise calculations, and ingenious engineering. The Romans did not defeat the laws of physics. They used them with a skill that still amazes us today. Aqueducts were not just infrastructure, they were the arteries through which the very life of Roman civilization flowed. They allowed cities to grow, supported hygiene, fed industry, and served as a powerful symbol of imperial power. From finding a source to distributing water in the castellum, each stage was thought out and refined to perfection. Today, when we turn on the tap, it is difficult to imagine the effort it took to bring water to the city 2,000 years ago. The history of Roman aqueducts is a timeless reminder that great civilizations are built on great engineering and the ability of humans to subdue nature, not by force, but by intellect. What do you think about this incredible achievement of the ancients? Which part of the history of aqueducts, the search for water, the calculation of the slope, or the construction itself, impressed you the most? Suggest topics for future videos about the great engineering projects of the past that you would like to see in the comments. And of course, don't forget to subscribe to our channel so you don't miss out on new exciting stories.